There is a formula. It may seem simple and concise, but at the same time, it connects the world of imaginary and real numbers in a fascinating geometric form. Its name is Euler's Formula. In this video, we will thoroughly explore the incredible features of this formula, and most importantly, we will explain how to derive it. The author will present it in the simplest way possible, step by step and visually. To begin, in order to fully grasp this formula, let's cover some basics and examine certain rules and limitations. Let's start by looking at the complex plane. It is a two-dimensional plane where real numbers are represented horizontally and imaginary numbers vertically. The properties of imaginary numbers are quite simple. The product of I multiplied by I is equal to -1. Additionally, if you want to multiply 2i by 3i, you can multiply their magnitudes or sizes, just like I, resulting in -6. With these rules, we can create quite intricate combinations. Returning to our plane, complex numbers are called complex for a reason. They consist of both an imaginary part and a real part. Graphically, a complex number on the plane is represented as follows. We plot a certain number of units horizontally for the real part, and then another certain number vertically for the imaginary part. It's important to note that these parts cannot be mixed, so they are expressed as the sum or difference of one part and the another. Notice that just as we cannot mix or combine them as numbers, graphically, the horizontal part cannot affect or distort the vertical part, and vice versa. Now the question arises, how do we multiply complex numbers? We will address this shortly. For now, let's consider other concepts: sine, cosine, triangles, and circles. Let's imagine that there is a circle depicted on the plane, with its center coinciding with the origin or the intersection of coordinates. Then the segment drawn from the center to any point on the circumference will be the radius. If we extend, or let's say drop an imaginary rope to the horizontal line, and rotate our drawing while doing the same with another surface, we obtain two perpendiculars called sine and cosine. They have some useful functions. Firstly, since they are ratios or coefficients, they are not independent numbers, whereas the hypotenuse or radius of the circle generally has a length of 1. Note that the lengths determined by sine and cosine never exceed the radius. Thus, sine and cosine never exceed 1. Another property directly follows from the Pythagorean theorem, as the radius can be considered the hypotenuse, and sine and cosine as the legs of a right triangle. The author recommends watching a previous video from this channel where this theorem is proven. It is also worth mentioning how angles are measured. You are probably used to degrees, but in this case and from now on, angles will be measured differently. For example, take a radius and simply wind it around a circle with a radius of 1. Then you will have a certain segment, or let's say a piece of pie. And the angle of this piece will be approximately 57 degrees, or exactly 1 radian. This is essentially its definition. It is quite simple, and even more convenient than measuring in degrees, as this measure is linear. For example, if you increase the length of the arc by 2, the angle will double. Moreover, if you measure 2 pi radians, it will be a complete circle, which corresponds to 360 degrees. Pi radians equals 180 degrees, and so on. Now the author thinks we can proceed to the consideration of the formula itself. And this formula, besides its super famous specific example, possesses almost magical properties. It is written as follows. Should be mentioned in advance that it's not exactly the formula itself, but rather its extended form. But don't worry if you don't understand it yet. Let's look at some examples instead. The first, the most famous one, e to the power of I pi. Pay attention to the structure of the formula here already. In this example, the exponent contains only the imaginary part I pi. There is no real part, or better to say, it equals 0. That is, e to the power of 0 plus I pi. If we represent this on our formula, we first need to raise e to the real part, which is 0. It will result in 1. Then, using the second part, we map this obtained radius to the angle pi. Since according to the formula, we need to substitute the imaginary value into sine and cosine. By rotating the radius by 180 degrees, or pi radians, or half a circle, we obtain -1. But wait. Here we can observe that magical property of this formula, separating the real part from the imaginary part. Let's modify our formula. What do you think will happen if we raise e to the power of 1 plus 2 trillion and 1 I pi? It may seem like the number should be colossal since we have an exponent, and moreover with a huge value. However, if we think about it a little, we can calculate that the answer is -e. Remember, we take the real part, raise e to it, and thus obtain the radius or length. Then we take the imaginary part and consider it as a thread of the same length as this imaginary part, in this case 2 trillion and 1 pi, and as if we wind it around a circle with a radius of 1. As a result, the radius will complete 1 trillion and a half revolutions and end up at the point -1 times e. In the end, -e. For example, if we take the number e to the power of 20 plus quarter pi I, the number in terms of magnitude will be quite impressive, as the length is e to the power of 20, which means the radius will be approximately 485 million. However, if we look closely, the complex part equals quarter pi or 45 degrees, and this is an angle at which sine and cosine are equal. By solving the problem with the Pythagorean theorem, we obtain approximately 345 million plus 345 million pi. But agree, it's simply inconceivable how the constant e raised to a complex power can separate them in such a whimsical way. Namely, that the real part is responsible only for the radius, and the complex part is responsible only for the angle without any mixing. Moreover, this rotation is performed according to very simple rules. We take the complex part and wrap it around a circle with a radius exactly equal to 1, not any other whimsical constant, thus obtaining the angle. Everything is precise and clear, miracles in a word. Well, a rigorous proof of this formula is not the easiest. You will have to study a considerable amount of topics to prove it rigorously. But what the author doesn't like is that the method of approaching this formula seems like juggling with formulas. From limits to derivatives, from power series to the relationship between the exponential function and sine and cosine. In this video, however, the author will try not to prove it completely, but rather show another, in his opinion, simpler way, albeit without proofs. Secondly, many rigorous definitions will be omitted, and he will ask you to take his word for it several times. So yes, this is most likely not a proof, but there is a hope that after watching this video, you will see it in a completely different light. But first, let's go back to complex numbers. Remember you were told that we need to learn how to multiply them? Well, it's not difficult at all. Let's start with simpler cases, multiplying a complex number by a whole number. In this case, you simply multiply each component by that whole number. In other words, scale it. If you multiply a complex number by an imaginary number, it's still a scaling, but the real part becomes imaginary, and the imaginary part becomes negative real. Now let's consider the multiplication of two complex numbers. Essentially, it's not too complicated either. You can think of it as a combination of the two multiplications we already know. Multiplying a complex number by its real part, then the same number by its imaginary part, and finally adding these two numbers together. You can practice multiplying some examples if you'd like. As mentioned before, any complex number can be represented on the complex plane by plotting its corresponding coordinates. But let's try another approach. Take any complex number already plotted on the plane. The line that connects complex number point with the origin and its distance will soon become very important for us. Next, let's imagine that we have a circle centered at the origin. In addition to the fact that the complex number will always lie on it, the plotted coordinates with the distance form a familiar right triangle with sine, cosine, and radius. Notice that just like we can find sine and cosine given an angle, we can also find the angle given sine and cosine. In other words, we can represent our number not only as plotted coordinates, but also as a radius of a circle positioned at a certain angle. Well, you may ask, what's so special about that? We simply changed the way we define numbers on the plane. But wait, when we start multiplying these numbers, magic happens again. To multiply two such numbers, all we need to do is multiply their radius lengths and add their angles. For example, if the first complex number is represented as a radius of 10 at an angle of 0.3 pi radian, and the second one as a radius of 5 at an angle of 0.6 pi radian, then their multiplication will result in a radius of 50 at an angle of 0.9 pi radian. Moreover, if you convert these two initial numbers into Cartesian notation, multiply them, and then convert the resulting number back into the notation of radians and angles, you'll get the same answer. But how is that possible? Well, to understand how this happens, a couple of tricks in the addition formula will be the best approach. Let's start with two simpler examples. Multiplying a two-dimensional number by a one-dimensional number. Multiplying a complex number by a real number is quite simple. Both coordinates simply stretch by the same factor as the real number. However, when it comes to multiplying by an imaginary number, things get more interesting. If you multiply it by I, each of the coordinates that make up the base of the complex number rotates by half pi radian and then stretches. But wait, if you multiply by a negative number, each coordinate will rotate not by half pi but by whole pi radian and then stretch. If you multiply by a negative imaginary number, the rotation will be 1/2 pi radian. And finally, if you multiply by a positive whole number, it will be a full circle rotation, but it will be as if there was no rotation at all. But how does this work? The answer is quite simple. We essentially set it up ourselves by defining that moving counterclockwise by half pi radian, I increases by 1 degree. We arrange these numbers and directions in such a way. But what about multiplying two complex numbers? As already mentioned, the sum formula and a slight digression will help. Given the condition sine alpha plus beta and cosine alpha plus beta, what formulas can we create for them if we only know sine alpha, sine beta, and cosine beta separately? How should we arrange them? What sign should we use? Let's consider this on a circle. Suppose we have two angles and the triangles formed by them, whose sides are known, and we denote them as the sines and cosines of the angles. Let's plot them on a unified circle, then start rotating one of the triangles so that one lies on top of the other, thus forming a new angle, alpha plus beta, and we can construct a new triangle whose sides we are trying to find. Next, let's construct a very interesting rectangle. First, we will start reducing the lower triangle until it touches the point of the second triangle. How many times do we need to reduce each of its sides? The answer is given by its hypotenuse. Before the reduction, it was equal to 1 or the radius. And now it is the same as the leg of this triangle, which is cosine beta. Therefore, we need to multiply the hypotenuse and each side to maintain the triangle's shape. Then, let's duplicate our first triangle, place it here, and so to say, reverse its reduction, restoring its original sides. Pay attention that there will be no bends at this point, just a straight line. Why? The answer is quite simple. In each triangle, the sum of all its angles is pi radian. In this case, we have right triangles, so these two angles are by definition equal to half pi radian, and the other two angles together will also add up to the remaining half pi. This means that this angle, let's call it x plus angle alpha, is equal to half pi radian. And in the end, we get this angle x plus the same alpha, because it is our duplicated triangle plus another half pi of this triangle. This gives us the same whole pi radian, or simply a straight line. This allows us to easily scale our duplicated triangle, reducing it until these 2 points coincide. Now we ask ourselves, by how much do we need to reduce the sides here? Again, the answer lies in the hypotenuse. Initially it was equal to 1, but now it is equal to the side of this triangle, which is sine beta. Therefore, all the remaining sides need to be multiplied by sine beta. Finally, the right-angled triangle we constructed from the beginning with angle alpha plus beta can be rotated by half a turn, and the sides will not change. The vertical cosine will remain the same, and the horizontal part, sine, will simply be shifted upwards. As a result, we obtain a rectangle. And you may ask, so what? However, all the answers are already written on this rectangle. Let's ask ourselves again, what is cosine alpha plus beta equal to? Look, here it is. If you look closely, you will notice that it, along with this segment equal to sine alpha times sine beta, is equal to the entire lower segment, cosine alpha times cosine beta. To obtain it, we need to subtract the small upper segment from the lower one. Now, sine alpha plus beta. This segment occupies the entire vertical side, and to obtain it, we need to add the two sides, sine alpha times cosine beta and cosine alpha times sine beta. So, we have these addition formulas. Let's set them aside and see what happens if we multiply two complex numbers represented as radii under angles. We can represent the multipliers by extending the radii in one direction and multiplying the brackets. We will get the sum of four combinations of multiplication. Cosine alpha times cosine beta plus cosine alpha times I sine beta plus I sine alpha times cosine beta plus I sine alpha times I sine beta. In this expression we can cancel out the multiplication by I, but the sign will change to minus. Now let's place the real or horizontal parts. Cosine alpha times cosine beta minus sine alpha times sine beta in the left part, and the imaginary or vertical parts multiplied by I sine alpha times cosine beta plus cosine alpha times I sine beta in the right part. Does it remind you of something? Let's recall the formula we derived recently. And we see that what we have in the left part is precisely the formula for the cosine, the horizontal part, and in the right part is the sine, simply multiplied by I. We substitute our values into these parts, and as a result what we have is that multiplying two numbers is simply multiplying the lengths of their radii and adding their angles. Notice that when multiplying the sines and cosines of complex numbers, the appropriate four combinations appear, which fit perfectly into our rectangle. And remember the fact that multiplying by I or minus I is simply a quarter-turn rotation? So by multiplying the imaginary and real sines and cosines, we obtain these sides that are rotated in different directions. From the formula we obtained, what the author calls the heart of Euler's formula emerges, the de Moivre's formula. If, for example, you multiply a number by itself 5 times, it is essentially the same radii multiplied by themselves 5 times, and the angle grows by a factor of 5 accordingly. If you raise a complex number to the power of 200, you will get a radius to the power of 200 and an angle 200 times larger, and so on. The second ingredient we need are limits. A strict definition and analysis of limits for understanding Euler's formula, in author's subjective opinion, are not required. So let's go with rough definitions in the spirit of repeat after me. So, the first example. Translating it from Math English, if n tends to 0, then, so to say, the reciprocal expression 1 over n will tend to infinity. Another example. Here it's pretty simple too. It doesn't matter what n tends to, as both the numerator and denominator contain n, so they cancel each other out, leaving 3 over 1, which is simply 3. Another example. Since n squared tends to infinity faster than 2n, it wins this so-called tug of war, and the entire expression becomes 2 over n, which equals 0. There are more interesting cases, but these examples are sufficient for a general understanding of the mechanics. Now, on to two other interesting cases from which we cannot escape. What do you think this limit equals to Remember that x represents an angle in radians if you recall correctly. This question means that if we have a circle with an arc and a perpendicular line, as the angle decreases and decreases, by how much will the perpendicular line be smaller than the arc? The correct answer is that it will be equal to 1. In other words, they will be the same. Actually, this limit is usually proven through formula joggling and the arc collapsing between two lines, sine and tangent. But now the author will ask you to believe him, that the limit equals 1, because he hopes that visual explanation is enough to demonstrate that sine and arc are getting similar with decreasing angle. Remember this limit, it is very important. The second very important limit, perhaps more familiar to you. It is remarkable here that if we carefully examine this formula, we encounter another tug of war. On one side, the exponent to which we raise tends to infinity, and thus the number. But the base, or the expression in parentheses, tends to 1, and even in an infinite power, 1 remains 1. So what will the answer be? Which force will win? The correct answer, which some or perhaps many of you already know, is that the limit is equal to Euler's number, approximately 2.71, etc. And here the author will ask you to take his word for it, because one can only approach this number infinitely, similar to the number pi. And to question why precisely 2.71, in his opinion, is like questioning why pi equals 3.14. Let's examine this second limit in more detail. What will the limit be if we have not 1 in the equation, but 2, 3, or 10? It would be more convenient, surprisingly, to impose additional conditions. Allow to explain. Imagine that the only parameter we can control is the growth rate of n. So if we increase the numerator in the fraction by, let's say, 2, then we must also increase the growth rate of n by 2 for that purpose. But in that case, n as a power on the outside will also grow twice as fast. Through transformations, we get that instead of e to the 1, we will have e to the power of 2. Or conversely, for example, if the exponent decreases by 4 times, then we need to decrease the growth rate of n accordingly by 4 times, resulting in e to the 0.25. And if the number is negative, the sign of n should also change. Now, finally, we can combine the knowledge we have gained so far. Let's try to raise e to some complex number. But we already know that it is the same as if we replace x in this limit with our complex number. Next, we need to consider that the entire expression inside the brackets is one complex number, since we add 1 to the initial complex number, which can be considered as the real part of the new complex number. However, this entire expression inside the brackets, being complex, is subsequently raised to an increasing power. So we recall the de Moivre's formula. Thanks to the specifics of this formula, we can and even have to calculate the radius and angle of the final value separately. First, the radius of the initial complex number plus 1. To do this, we need to calculate the distance of this segment, which is the sum of distances. What will this distance be? The length of this segment can be calculated using the same formula from the Pythagorean theorem, but with a trick, because this formula can only be applied to right triangles. In this case, the right triangle will be formed by 2 legs. 1 unit segment plus real part over n, and imaginary part over n. Substituting into the formula, we get square root, and under the sign of square root will be 1 plus real part over n squared plus imaginary part over n squared. Expanding the squares inside the expression, we get 1 plus 2 times real part over n, plus real part squared over n squared, plus imaginary part squared over n squared. Now, if we imagine that this expression, when raised to the power of n, should result in something related to the number n, in this case only 2 times real part over n will have a value, because everything else except 1 is divided by n squared, which pulls them closer to 0 more strongly than just n. And if with a simple n there is an influence on the final result, in this case their influence will be 0, which means that only these numbers affect the length or radius. And now if you look closely, this too is in the numerator, so let's remember how we considered this limit and multiply it by the power outside. The square root sign on the outside and the 2 on the inside cancel each other out. And in the numerator, only the real part remains. But in the end, we have a formula from the second limit, and we know that the numerator is the number to which the number e will be raised, which means that the radius or length is equal to e to the real part. Now the second part of the de Moivre's formula, the angle under which this radius will be. If we attach a complex number to the horizontally placed unit and then decrease it, but at the same time raise the general number to an increasing power, unexpected values will come not only for the radius, but also for the angle. Notice that we are doing the same thing, and we have a right-angled triangle again with a vertical leg of length imaginary part over n. But let's draw an arc next to it and denote some angle. Remember how we mark angles. We wind segments of certain lengths around a circle with a radius of 1. Furthermore, since the imaginary part tends to 0, this arc and the imaginary part will be equal. So this arc, representing the angle, will also be equal to imaginary part over n. Thanks to the de Moivre's formula, by raising it to the power of n, we lay down these tiny angles equal to the imaginary part over n times, which means they simply cancel each other out. Thus, we take the imaginary part, decrease it by n due to the first limit, as if this vertical leg transforms into an angle, and then increase this angle back by n. But since it is already an arc or an angle, in the end, we essentially take this imaginary part and wind it around a circle. Finally, we obtain a radius with a length of e to the real part at an angle equal to the arc or imaginary part wound around a circle with a radius of 1. Let's go back to the example with pi. The real part is 0, and the imaginary part is pi. In the case of the radius inside the second limit, there is only 1. Everything else either becomes 0 or decreases too quickly. 1 raised to the power of n equals 1, which is the length of our radius. And the imaginary part, which was divided by n and due to the first limit transformed into an arc, is stretched back n times around a circle with a radius of 1. And this is a half revolution. With a length of 1, we find that the radius falls on the point -1, which means e to the I pi equals -1. You can try it with other examples, including those mentioned earlier. In the meantime, the video has come to an end. The author hopes this work has clarified many useful things for you, and for those who could easily prove it rigorously and found this footage rather boring. This most likely just means that the topic discussed in the video was too simple for you.